Hi, I'm Yiming Zhang from Tsinghua University. Today I will present our study on the hidden roots ecosystem. This is the joint work with researchers from UC Irvine and Tsinghua 360. For short, this paper concentrates on the client-side root certificate stores, or more precisely, on the roots excluded from public programs, but trusted by real-world clients, termed as hidden roots. We reported the first large-scale measurement of this ecosystem by collecting over 1 million hidden roots from real-world volunteers in 5 months. Our analysis uncovered the scale, activities, and impact of the hidden roots, and exposed the implementation flaws, which could be critical for Web PKI security. Let's start by reviewing the trust model of Web PKI. The authentications between peers are protected by digital certificates, which are queried from certificate authorities and signed by the root or intermediate root certs. The whole chain would be sent from web server to the client, and the connection is authenticated only when the root of the chain is trusted. Currently, mainstream operating systems and browsers maintain their own trusted root lists, known as the root stores, such as Mozilla, Microsoft, and Apple. Root certificates in these stores all have been strictly evaluated and well supervised. However, the official root store is not equivalent to the actual one used in the wild, as it would be modified by various entities, including local software like VPNs, enterprise or government network operators, or by malware. Trusting root certs outside public lists could be risky, as their behaviors are not publicly visible. In recent years, plenty of vulnerable cases have been reported. Local software would act as the man-in-the-middle attacker to intercept traffic by implanting their own routes. Governments would also abuse the routes to monitor web users. In this work, we term these root certificates outside public programs will have been implanted into local stores and trusted by web clients as hidden roots. Although plenty of studies on certificates have been published, they concentrated on the public ecosystem, leaving hidden roots ill understood to the community. This paper aims to uncover this ecosystem from the real-world web client's perspective. We answered a set of research questions, including what's the scale of this ecosystem, how much traffic, and how many clients are impacted, who are the operators of hidden roots, how are the hidden roots performing in certificate issuance and management, and are there implementation flaws of them and the issued certificates. We fill this knowledge gap by collecting and analyzing large-scale certificate chains with their verification results on real-world clients. We collaborated with 360 Secure Browser for data collection. It is a leading PC browser with over 100 million monthly active users in China. When one volunteer user visits a website through HTTPS, the browser does 2 checks on the certificate chain. The first one is the regular verification, by calling the API of the operating system, such as the crypto API on Windows, and logs the results to a status code. Each bit of the code indicates one type of error, such as common name invalid and date invalid. Particularly, the authority invalid bit reveals whether the root is located in the client-side root store. Besides, the browser further checks whether the root is public by searching it in these 3 major public stores and records the results with a public trusted flag. The certificate chain would be collected from the clients when the public trusted flag is unset, or at least 1 bit is set in the status code. That is, the browser only collected invalid chains and chains that link to hidden roots. The dataset is collected from February 1st to June 30, 2020. Together with the chains and the two checking results, an anonymized client ID, the host, and timestamp would also be reported, as shown in the example. Besides, considering the chains would be disordered or incomplete due to possible misconfigurations or network errors, we take additional steps to filter out the root certificates according to RFC standards, as shown on the slides. If one cert from a non-public trusted chain satisfies all criteria of a root cert, it would be considered as a head root. Our next question is, who owns the head root? However, accurately inferring CA ownership is a hard task, even for those in public stores. Mozilla's Common CA database provides the most comprehensive ownership information. Well, it could not facilitate for this research, as all our rules are beyond the public view. Therefore, we followed the best practice of previous studies, leveraging subject distinguished names to classify certificate groups and infer ownership. We also identified templated root by a server log parsing algorithm. Specifically, header roots with an identical or templated site of common name, organization, and organization unit could be roughly grouped and considered held by the same organization. We first give an overview of the dataset. Totally, 222 million chains that link to header roots were collected during the 5 months. Their daily traffic and statistics of validation results are shown in the figure. Over 1 million distinct header roots were identified, and we found that they have been widely implanted into the local root stores. By inspecting the traffic logs, we found over 1 million FQDNs have been affected. We also utilized the client ID, the hash of the timestamp, when a volunteer joins the data collection program, to give an estimation of web clients. In total, about 50.7 million volunteer users have been witnessed header roots. Besides, the certificate grouping algorithm produced 5,005 hidden root groups. The roots in one group are considered to be held by the same organization. The size and impact distribution of the groups are shown in the figure, which is as expected as a long-tail distribution. We also take a closer look at the big groups, taking the top 100 groups as the benchmark to explore the activities and sources of header roots. We define the active time of a group as the number of days when their roots were captured in our dataset and further qualify their stabilities. And interestingly, we find the ecosystem is dynamic and updating. That is, we both observed new emerging header roots and returning ones. The figure shows typical examples we found from the top 100 groups. The red box circles to returning groups. The traffic dropped to 0 at the end of our observation period. Take BJCA as an example. Its traffic mainly came from a government website. However, in April 2020, the website changed to use certificates signed by a public root. Since no other websites use BJCA to issue certificates, at least from our point of view, it has been retired. In contrast, the 3 groups at the bottom of the figure are emerging ones, with the number of their certificates, their daily traffic, and the number of web clients trusting them are all on the rise. As our observation only lasted for 5 months, we believe longer-term observations of the ecosystem may reveal more exciting insights. Then we manually identified the category of hidden CA groups by inferring the semantic of the subject fields together with searching keywords and hash values in search engines. Totally, 85 of the top 100 groups are identifiable and fall into three main categories: self-built routes, fake routes, and local software routes, as shown in the table. The other 15 groups were classified as unknown due to the lack of identifiers. Despite not being recommended by the security community, we found self-built CAs are still widely used to issue website certificates covering over 3,000 FQDNs, mainly by organizations like government agencies and enterprises. However, they do work disappointingly, with over 75% of the chains issued being invalid for various reasons. One may suspect that self-built CAs are primarily used in the internal network, thus their security impact would be limited. However, through active scanning experiments, we confirmed that over 70% FQDNs that using self-built CA issued certificates were providing public network services. Another category is referred as fake certificate authorities, as they impersonate trusted CAs with deceptive subject names, as shown in the table. They either replace characters in authentic CA names with homographs, or simply extend the words. Hidden rules from fake CAs have infected a wide range of almost 2 million HTTPS connections and highly gained the trust of clients. Uncovering the real owners behind the fake routes is quite challenging, as their subject names are deceptive and we did not collect any other identification information except for the certificates. As the best effort, based on the intelligence reports and sandbox from security companies, we found one fake route associated with Trojan and 43 fake routes associated with malware, such as CoinMiner or adware. This evidence strongly indicates the relationship between the fake routes and malicious parties. Nevertheless, we also speculate hidden routes in this category may come from spamming tools or free applications that irregularly intercept user traffic in an impersonated manner. We also found 24 of the top 100 groups are held by local software, including packet filters, VPNs, proxies, security software, and parent control applications. Previous study recognized the local applications as the dominator of HTTPS interceptions, while in our dataset, the percentage of traffic from local software is quite low. As for the reasons, for the one hand, there may be several local applications with non-identifiable subject information and being misclassified as unknown by us. But on the other hand, as our observation is taken from a novel, passive, client-side perspective, our results may better reflect what happens in the real-world clients. As discussed above, hidden routes have been widely trusted by real-world clients and influence a huge amount of web traffic. Well, how do they perform in certificate issuance and management? What are the security risks of trusting them? We answered these questions by analyzing the implementation flaws of the ecosystem. First, we found a series of certificate misusages. Over 97% of the chains were sent directly by the routes, rather than intermediate ones. It may be reasonable for local software that needs to send certificates in real time. However, we also found over 40% of self-built CAs would directly send certificates for websites providing public services, which seriously violates the security recommendations. Besides, we found 144 hidden groups share the same public key across all their hidden routes, which increases the risks of being compromised. Surprisingly, Two security software have also been found for this mistake, sharing the same public key among more than 7,000 root certs they hold. We also found that hidden roots behaved quite confusingly on the settings of certificate validity. This figure plots the creation dates and expiration dates of hidden roots. We found dozens of them even have unreasonable settings, for example, expiring at the year of 9999. Zooming into the roots created during 1980 and 2020, most of them have a valid period significantly longer than the best practice. Over 79% are valid for 60 years, and over 300 of them even for over 100 years. To compare, our rules in public programs are valid for less than 40 years, with a median of 20 years. Therefore, the security risks may last long for clients trusting hidden roots. We also manually collected a list of 116 roots that have been revoked by public programs, and found 23 of them were still active in our dataset, trusted by over 34,000 clients and influencing over 200,000 HTTPS connections. We further analyzed the content in compliance by the lint, a linter that checks whether the content of a certificate meets implementation requirements. We first check the hidden roots themselves, as shown in the table. Over 87% of them have been reported at least one error. Most of them miss critical extensions as the key identifiers. Besides, invalid or vulnerable settings are also prevalent. For example, they would still use weak algorithms like SHA-1. We further checked the content of leaf certs issued by hidden roots, and found the results are even more terrible. On average, the lint reports over 8 errors on each leaf cert. 85 of the top 100 hidden CA groups even sent every their leaf certs with implementation errors. The performance is significantly worrisome compared with public trusted ones. In summary, we take the first national client-side view of hidden roots. The inherent non-transparency of this ecosystem makes it hard to be well regulated and leaves security risks as reported in this work. Our study suggests the community to review the security of local stores in the wild and seek a better practice to regulate and manage hidden roots. We also have made a few recommendations to mitigate this issue. For example, the operating system should regulate root store management by monitoring, logging, and promoting the users for third-party modifications. The browser is suggested to maintain public stores as whitelists and differentiate safety icons for links towards hidden roots. As for the local applications of benign usages, providing more precise subject information and normalizing certificate content would also be helpful. Thanks for listening this talk. Please refer to the paper for more details, and I'm also glad to take any questions at the conference. Thanks.